Welcome to 1 Black 3 Quanta. Today we are mastering AP Physics 1, starting with systems and Center of Massachusetts. First, what is a system? A system is simply a collection of objects that interact with each other. If the internal structure or moving parts of a system don't affect its overall macroscopic behavior, physics gives us a shortcut. We can treat the entire complex system as just one single object. But where do we place this single dot? At the center of mass. For perfectly symmetrical objects, it's located right on the lines of symmetry. But for asymmetrical systems, we calculate its position using this core formula. Let's visualize how this formula works in 3D space with a practical example. Here we have a 3 kg red mass and a 1 kg blue mass. Plugging their values into our formula gives us their exact balance point. It's at x equals -1. Notice how the center of mass stays closer to the heavier object. Topic 2.2 focuses on forces and free body diagrams. A force is a vector quantity that describes the interaction between two objects or systems. Remember, an object cannot exert a net force on itself. To visualize these forces, we use a free body diagram. In an FBD, the entire system is treated as though all its mass is located at the center of mass, represented by a single dot. Forces exerted on the object are drawn as straight arrows originating directly from this dot and pointing in the direction of the force. Let's add gravity, normal force, and applied force. Now, let's look at a 3D solved example to understand how to apply this. Let's map the forces on this 5 kg block. Gravity pulls down with 50 newtons. The floor pushes up with an equal 50 Newton normal force. An applied force pulls right with 20 newtons. Finally, kinetic friction resists with 10 newtons to the left. Here is the complete 3D free body diagram. Topic 2.3 Newton's third law. The core principle is simple. Every interaction between two objects results in a pair of forces. If object A exerts a force on object B, B exerts an equal and opposite force on A. An important conceptual rule: interactions between objects within the same system are called internal forces. These internal forces always cancel each other out, meaning they cannot change the motion of the system's center of mass. Let's observe this action-reaction pair in a 3D space with a practical example. Here is Newton's third law in action. Watch as block A pushes block B. The action is a 30 Newton force pushing to the right. Instantly, block B reacts with an equal 30 Newton force to the left. Equal and opposite. Moving on to topic 2.4, Newton's first law. This law introduces the concept of translational equilibrium. This happens when the net force exerted on a system is exactly zero. Mathematically, we write this as sigma F equals 0. This means all the individual forces acting on the object perfectly balance each other out. So, what is the result of this equilibrium? Newton's first law states that the system's velocity will remain constant. If it's at rest, it stays at rest. If it's moving, it keeps moving at the exact same speed and direction. Let's observe this constant velocity in action with our 3D example. Newton's first law states that constant velocity requires a net force of 0. Here, a 20 Newton applied force is perfectly balanced by 20 newtons of friction. As a result, the block achieves equilibrium and glides at a perfectly constant speed. Topic 2.5 focuses on Newton's second law. When forces are unbalanced, the net force exerted on a system is not equal to 0. The velocity of a system's center of mass will only change if a non-zero net external force is exerted on it. The equation is acceleration equals the net force divided by the system's mass. The acceleration is proportional to the net force, and it always points in the same direction. Let's observe this acceleration with a 3D solved example. Here is a 2 kg block pulled with 20 newtons, opposed by 6 newtons of friction. This leaves an unbalanced net force of 14 newtons to the right. Using F equals ma, we divide force by mass. The block accelerates at 7 meters per second squared. Welcome to topic 2.6, Gravitational force. Newton's law of universal gravitation states that any two masses attract each other. This force is proportional to the product of their masses and inversely proportional to the square of the distance between their centers. Near Earth's surface, this gravitational force on an object is what we call its weight, calculated simply as mass times the gravitational field strength, g. An amazing fact, the mass that resists acceleration, known as inertial mass, is experimentally identical to the mass that creates this attractive force, known as gravitational mass. Let's see this universal gravitation formula applied in a 3D solved example. Two objects, each 10 to the 5th kilograms, are 10 meters apart. Using Newton's law, we substitute the values to find a force of g times 10 to the 8th newtons. The inward yellow vectors confirm this is a mutual, attractive force. Topic 2.7 covers kinetic and static friction. Static friction occurs between contacting surfaces that are not moving relative to each other. It adopts the exact value and direction required to prevent slipping, up to a maximum limit. When the applied force exceeds this maximum static limit, slipping and sliding occur. Kinetic friction then takes over. The kinetic friction force opposes the sliding motion and equals the coefficient of kinetic friction multiplied by the normal force. Important properties to note. The coefficient of static friction is typically greater than the coefficient of kinetic friction. Also, the force of friction does not depend on the surface area of contact. Let's view the transition from static to kinetic friction in a 3D example. First, we determine the maximum static friction limit, which is calculated to be 20 newtons. Applying a 15 newton force fails to break this limit, meaning the block remains stationary. Increasing the force to 25 newtons exceeds the limit. The block slides, and weaker kinetic friction takes over. Topic 2.8 covers spring forces and Hooke's law. When a spring is stretched or compressed from its equilibrium position, it exerts a restoring force that tries to return it to that neutral state. The equation for this is F_s equals negative k times delta x. The constant k is the spring constant, which measures the stiffness of the spring. Pay attention to the negative sign. It indicates that the spring force always points in the exact opposite direction of the displacement vector. Let's apply Hooke's law to a 3D solved example. Applying Hooke's law to a spring with a stiffness constant of 50 newtons per meter. Stretching the block 0.2 meters to the right triggers a restoring force. The calculation yields exactly 10 newtons pulling to the left, directly opposing the displacement. Topic 2.9 concludes this unit with circular motion. When an object moves in a circular path at a constant speed, its direction is constantly changing. A change in direction means a change in velocity. Because the velocity is changing, the object is accelerating. This is called centripetal acceleration, and it always points directly toward the center of the circular path. Notice the relationship between the vectors. The velocity vector is always tangent to the circle, making it exactly perpendicular to the inward-pointing centripetal acceleration vector. Let's observe these vectors in motion with our final 3D solved example. A planet moves in a 2-meter radius orbit at a constant speed of 4 meters per second. Squaring velocity and dividing by radius gives a centripetal acceleration of 8 meters per second squared. Notice how the green velocity vector remains tangential, while the red acceleration vector constantly points to the center. Next up, we will dive into work, energy and power. Subscribe so you don't miss out.